Okay, good. So, let's take a look at where we are so far and where we are headed, right. So, let's do a very quick recap of what we have studied so far. So, in the beginning, of course, we studied some basics of quantum information and so on. This is just to make sense of quantum algorithms, and then we saw a few quantum algorithms, right. So, we saw Simons, Deutsch-Josa and Bernstein-Vazirani. We saw a few of these algorithms, and I was trying to weave them together with this theme that really over and above randomized computation, the only thing that these algorithms are doing is this Fourier transform. Okay, so we did not define Fourier transform yet, we will define it today. Okay, but remember, like, we were applying the Hadamard gate, and then we were doing some computation, and typically we will apply it again and then we will do some measurement. And we saw that in these examples which we developed in class, we saw that this is helping us to get a significant speed up over the classical, even randomized versions of these algorithms. So, if you remember, back from when we were discussing this, I was saying that a main theme here that we are trying to understand, see, finally this is a computer science course. I mean, what that means is that the perspective is computational, right. So, the question is, how do you understand computation, how do you do computation effectively, right. And the main theme that I have been trying to bring us back to again and again is that the power that quantum algorithms have over classical randomized algorithms is the additional ability of an efficient Fourier transform. So, the Fourier transform on an exponential space can reveal some patterns in the output, which we can somehow then benefit from by doing a measurement. Okay. Now, if we were to try to do the same thing classically, it would take us exponential time. But the beauty of this is that in the quantum space, we can do this efficiently and still get something interesting out of it by measuring. This was the idea. Yeah. So, we started by looking at these algorithms. We did not formally unify them in this paradigm yet. So, the plan will be now to do that. Okay. So, starting from these algorithms, we then made a sort of a detour into cryptography, because, well, the title of the course is Quantum Algorithms and Cryptography, right, and the main place where quantum algorithms have had an impact is in the domain of cryptography. Yeah, so we talked about how, well, cryptography is based on the hardness of some underlying problems, and these problems need to have some sort of structure for them to be useful in cryptography. So, we saw the various hard problems like the RSA problem, factoring problem, discrete log problem, Diffie-Hellman problem and so on, right. And the goal from these problems is sort of twofold. One is to, of course, see why they are useful, and in showing you why they are useful, what I am hoping is coming across is that the algebraic structure is kind of really necessary. So, remember, we saw encryption schemes, right, we saw key exchange and we saw encryption. So, this is not a full cryptography course, we did not do that much, but the goal is to say that, okay, at least for some kind of fundamental cryptographic primitive such as encryption, right, this is how you do it, and then this is how you you do the reduction of security. So, you should be able to argue that breaking the crypto system is at least as hard as solving some underlying problem like factoring or whatever, right. So, the goal there is to, among the goals there I should say, is to understand that this algebraic structure was really necessary. So, for the case of an encryption scheme, you do need to finally decrypt. Yeah. So, you need some algebraic structure over there. Is this making sense to everybody? Yeah, so you need some algebraic structure, and it turns out that some of this algebraic structure is going to fall prey to this Fourier transform, the extra power that is given by the Fourier transform. So, now what we are doing is we are actually circling back, right. So, we started with some quantum algorithms, right? We talked about how without proving anything about a Fourier like without even defining a Fourier transform, we talked nevertheless about how that is somehow happening. And then we went to see, first of all, what is all the fuss about with cryptography, right? So, what algorithms do we develop and use in cryptography? What are the hard problems there? And from today onwards, we will join these two threads. Obviously, they are very related, right? That is why we are talking about them. Now, we will join them. So, what we will do is we'll define the Fourier transform. It is about time, right? So, we will define the Fourier transform both over Z2 and over Zn, and we will see how the Fourier transform has been playing very fundamental roles in the algorithms that we saw so far. Okay. So, we will briefly touch upon the algorithms we saw so far. It is mostly something that you need to do offline on your own, but we will touch upon why it was really the Fourier transform that was giving us the extra power. We will see another very important illustration of the Fourier transform, which is very relevant to cryptography, called Grover's algorithm. So, this is an unstructured search problem. We'll look at that, and then we'll finally look at Shor's algorithm for factoring, right, for period finding, and this will break both factoring and discrete log. So, what we will have done is we will have seen how the extra power afforded by this Fourier transform is actually going to hit us exactly where it hurts in cryptography. So, these mainstream crypto systems will be broken. Okay, so, that is the goal for the next 2 weeks, and then subsequent to that, of course, we will clean up after ourselves. So, then we will look at problems that withstand quantum attacks. We will discuss why they are believed to withstand quantum attacks, and we will rebuild cryptography from some of them. So, this is like a minimum thing that we will do in the course. Time permitting, we would love to do sort of we would love to develop some ideas of how to use special properties of quantum computing also to build cryptography, not just to break classical cryptography, but also to build cryptography. Okay. So, to begin with, let us finish our discussion of RSA crypto system. Yeah. So, if you remember, we talked about proving the security of RSA in the random oracle model. So, a very quick recap, we already did this last time. So, the random oracle is a box that will take some binary string as input and give some output. The internal workings are unknown and inscrutable. So, this is why it is called an oracle. Basically, you only access it via input output behavior, nothing else. It is consistent. So, if you query it multiple times on the same input, you get the same output, and anyone can interact with it. The random in the random oracle means that for any given input, the output will be distributed uniformly over the range. Okay. So, it will give a random output. And yes, because of this reason, it is hard to invert by definition. Okay. All right. So, recall the RSA encryption scheme that we had in the ROM. So, because it's a new week, I will remind everybody of the scheme. So, here we are using a hash function h, which is modeled as a random oracle. Okay. And now let us remember keygen encrypt and decrypt. So, keygen, it runs this gen RSA, which outputs N, E and D. So, by now everyone is an expert on what this is. So, here the PK is going to be N and E, and the secret key will be N and D. So, in general, the secret key can be assumed to include the whole public key, but yeah, here we are writing some of it explicitly. Now, in order to encrypt some message m, okay, so let us say that m is of length L. So, what did we do? So, we sample a random R, okay, and then you compute R to the E mod n, okay, and H of R XOR m. Remember this? So, we had some discussion on, it is actually a very, very nice scheme. I mean, it's maybe hard to appreciate in the beginning why it is the way it is, but it's a great scheme. I mean, it's also very famous, of course. You know, remember that the reason we are sampling this random R from the point of view of security is that, of course, one thing is that the encryption needs to be randomized. We've already talked about that quite a lot. But aside from that, you know, why a random R? Because if R is random, then you know, the RSA assumption anyway, it will tell me that given R to the E mod n, I cannot compute the whole R, right. And if R is random, then this means that even if the attacker has access to the random oracle, which it will have, the chances that it will query the oracle on this particular R will be negligible, right, for a sufficiently long R. And now even if R to the E mod n were to leak some partial information about R, let us say it leaks, you know, half the bits of R, suppose, even then H of R will nevertheless be completely unpredictable. So, there is a very sort of clear reason for why it is being done exactly in this way. And now how do you decrypt? So, you know, when you decrypt, of course, you have D and you have the ciphertext. So, what will you do? So, first you will, you know, invert RSA and get back R, right, and then you compute H of R and get M, yeah. So, proof of security. So, the theorem that we want to prove is that you know, if RSA is hard, relative to Gen RSA, and H is modeled as a random oracle, then the scheme that we constructed satisfies int CPS security. Okay. So, this is our theorem, and I want to go over the proof, you know, at least at a high level, because yeah, it is important to see the formal argument. Okay. So, let's do the proof. So, you know, let's say that A is our adversary, okay, and consider the following game, right. So, let us call the scheme as pi. Okay. So I'm recalling the int CPA game with the random oracle in it. Okay, so we've talked about the game itself. So I'll just go over this quickly. So here what happens, you know, a random function h is chosen. Then gen RSA is run to get n, e and d. Okay. A is given pk, which is, you know, n, n, e. And may query h. At some point A outputs two messages M0 and M1 of L bits. Now a random bit B is chosen and R is chosen. A is given, you know, R to the E mod n followed by HR XOR M, MB. Okay. A may continue to query H. And then A outputs a bit B prime. So, the output of the experiment is 1 if B prime equal to B and it is 0 otherwise. Okay, so this is our game, and let us define epsilon as, you know, the probability that the output of this experiment is 1. So, I went over this a little bit quickly because we have already done this. Yeah, so but just to set up the, like, to write down the proof, I want to make sure everyone remembers what's the scheme and what's the definition. Okay, good. So this is what you know, this is what we have, this is our game. And what do we want to show? We want to show that you know, as long as the RSA assumption is true, then our scheme satisfies in CPS security, right. So in particular this epsilon, we should be able to upper bound it by what? Negligible? Half plus negligible, that is exactly right. Okay. So let's set up a little bit of notation. So let query denote the event that A queried R to H. Okay, so you know, there is obviously some probability that A will query the random oracle with R, in which case security will be completely broken, right. So let's say that query is the event that A queried R to H. So now let's try to yeah, and you know, let success be the event that the output of this experiment is 1. Okay. Okay. So, now what is the probability of success? So, this is obviously the probability of success and query bar plus probability of success and query. Yeah. Okay. And this is probability of success and query bar plus probability of query. Everyone agrees? Yeah. So, either you queried or you did not query, right. So, we can just look at the two cases separately. So, now if I did not query, so let us see where this is headed, right. So, if I did not query the random oracle with R, then what is the probability that the the output is 1? It is exactly half. Why? Because if I did not query for R, then H of R is completely random by definition. So, then I have basically 0 information, then it is just a one time pad, right. So, then my HR plus M is just acting as a one time pad. So, there is no information whatsoever about B. So, if we are in this situation, then we are good. I mean, we can say that the advantage is half. Now, we have to worry about the probability of query. Now, intuitively, the reason we expect the adversary not to be able to query for R is the security of RSA, right, because obviously R is there in the ciphertext. So, this R is being hidden by RSA, right. So, what we will do is we will just write two claims here. So, if H is a random oracle, then the probability of success and query bar, this is exactly, this is less than equal to half. Okay. So, the proof we already discussed. In the interest of time, I will not write anything for this. The second claim is more interesting. So, yeah, if RSA is hard, relative to Gen RSA, and H is modeled as a random oracle, then probability of query is negligible. Okay. So, this is the more interesting claim. So, of course, if I did not query, then it is just like a perfect one time pad and I have nothing to worry. So, why, I mean why can I say that the adversary only queries R with negligible probability? So, this is basically just following directly from the security of RSA, right. So, what does the adversary see? It sees some information about R in the form of R to the E mod n, right. But by the security of RSA, this does not allow it to recover R. So, the probability that it can query R is just the probability that it can break RSA, right. If it breaks RSA, it can recover R and then make the query, right, or it can guess R. So, guessing is anyway negligible probability for sufficiently long R, right, and breaking RSA is negligible probability by security of RSA. So, a little bit more formally, so just a proof sketch here. Okay, so if query occurs, then one of A's queries satisfies R to the E is you know C1 mod n, okay, which allows us to output R as an answer to the RSA challenge. Hence, the probability of query is negligible as long as RSA is hard. So, you can solve RSA with the same probability that you can make the query, right. So, this suffices. So, to see a formal more formal reduction, in fact I should say formal reduction, because what we did is still not formal, I mean we are sketching the idea, right. I recommend you look at Katz-Lindel's treatment of this, right. There are of course many very good references out there. The notation I am using is from Katz-Lindel. So, is it clear to everybody? This is our scheme, and you know we proved that it's secure as long as RSA holds.